Let's talk about oxidation states. If we transform methane into chloromethane, then we have oxidized at the carbon. We've oxidized because chlorine is more electron withdrawing than hydrogen. It removes electrons from the carbon, and that's an oxidation process. Similarly, if we transformed chloromethane into dichloromethane, that's an oxidation reaction. If we then go on to trichloromethane or chloroform, that's an oxidation as well. Finally, we could go all the way to the highest oxidation state, that's carbon tetrachloride. So organic chemists might say that in transforming methane to chloromethane, we've risen by one oxidation state level. Chloromethane to dichloromethane, one oxidation state level, and so on. Or you could say, for instance, that chloroform or trichloromethane is 1, 2, 3 oxidation states above methane. It's a little bit more complicated to see when we replace hydrogens with other heteroatoms, because oxidation could be replacing a hydrogen with anything more electronegative. So if we oxidize methane by somehow replacing one CH with an OH, a carbon to OH bond, then we form methanol. So methanol is one oxidation state level higher than methane. If we oxidize methanol, however, we come to the hydrate of methanal. The hydrate of methanal and methanal itself are at the same oxidation level. So methanal is one oxidation state higher than methanol. If we add another OH in place of a CH, we form a molecule which would be CHOH 3 times, and of course that doesn't exist in that form. It loses water straight away, and we form a carboxylic acid. The compound CHOH 3 times and the corresponding carboxylic acid, which of course is methanoic acid, are at the same oxidation state. And similarly, if we were to make a compound formula carbon OH 4 times, that will decompose immediately to CO2 and 2 molecules of water. So CO2 is at the same oxidation state as carbon OH 4 times, and that's one oxidation state level higher than methanoic acid and one oxidation state higher than methanol, higher than methanol and methane in the same way. It's harder to see the oxidation states of something like methanol, formic acid and CO2 because the compounds exist in a different form, unlike the chlorinated forms of methane. Now in organic chemistry, we also have to consider reduction and oxidation between hydrocarbons with multiple bonds. So if I take ethane and somehow remove 2 hydrogen atoms, I generate ethene, and we say that is at a higher oxidation state than ethane. Similarly, if I take ethene and remove 2 hydrogen atoms, I get to ethyne, one oxidation state higher than ethene. Conversely, if I reduce ethyne to ethene, I've gone down in one oxidation state. Or if I reduce ethyne all the way to ethane, I've dropped it by 2 oxidation state levels. Ethene and methanol, for instance, are at the first oxidation level, and ethyne and methanal. Now, a word of caution here, this is just a formalism. Electrochemists will talk about redox potential for compounds. And is the redox potential of ethyne equivalent to methanol? No, of course not. They're not the same. And they would measure this in electrochemistry and tell you exactly what the values are. However, electrochemistry is a branch of analytical chemistry. Those people have a careful attention to details. In organic chemistry, we approximate the oxidation levels of things like ethyne, and methanal to be the same. In organic synthesis, organic chemists move compounds between oxidation states, like a musician moving between notes in a scale. Alkane, alcohol, aldehyde, acid, CO2, acid, aldehyde, alcohol, alkane. Can I join the band now? Thank you for watching. This is Kevin Burgess. If you want to see more videos in this series or purchase a book on organic reactions, please visit the website www.buyinquisition.org.